Hello, so we have here the xt, the vt, and the at equations for SHM. From these three, are we able to figure out the ax equation? How the acceleration varies with displacement? Yes, definitely. In fact, it's staring right at our faces now. Do you recognize x naught sine omega t? X naught sine omega t is x. So we just need to replace this thing with x. And we get a is equals to negative omega square x. Is that simple? So if we plot the ax graph, it's just a straight line graph passing through the origin. And in fact, the gradient of that straight line graph will correspond to negative omega square because the equation is that simple. Okay, let's try to appreciate what we've just discovered, yeah? So it seems like for SHM, the acceleration is directly proportional to its displacement. The velocity is not even in the picture. So the further away you are from the equilibrium position, the larger the acceleration. Now notice the negative sign here. What's its significance? It means that when your displacement is positive, your acceleration is negative. And when your displacement is negative, your acceleration is positive. In other words, when your displacement is rightward, the acceleration is leftward. When your displacement is leftward, your acceleration is rightward. Which means the acceleration is always directed towards the equilibrium position. That's the neatest way to put it. Now it's very important that you internalize this fact that for SHM, the acceleration is directly proportional to your displacement and always directed towards the equilibrium position. Now I need you to notice that when the oscillation is at its extreme position, that's when the springs are most stretched. I hope that gives you the feeling that the acceleration is strongest at the extreme positions. And when the oscillation is at the equilibrium position, because the two springs are equally stretched, the net force is zero. That's why the acceleration is zero. And you have to notice that the acceleration is always towards the equilibrium position. The velocity doesn't matter. So for example, if whenever you're at this position here, the acceleration is always towards the left, towards the equilibrium position. And whenever you're at this position here, this position, the acceleration is always rightward, again towards the equilibrium position. So the velocity doesn't matter. Whether you're going leftward or rightward, the acceleration is always towards the equilibrium position. What it does mean is that whenever you're moving away, you slow down. And whenever you're moving towards, you speed up. Yeah? So speed up, slow down, speed up, slow down, speed up, slow down, but the acceleration is always towards the equilibrium position. Okay, that's all. Ta-ta!